screen. Let that recording icon appear. Yeah. Okay. So this is what we did in the previous class. We looked at the local field potential data. This is how it looks like. It's a 76 cross 4096 array. Each point sample here is one time value, and this is just voltage in microvolts. If you average the signals, this is the trace that you get. It's called the ERP. 0 to 400 milliseconds is when the stimulus is presented. So this is the ERP, and it matches well with the onset of the stimulus and increase in firing rate and so on. These were the questions that we asked. Are there any oscillations in the local field? Is the power of these oscillations changing with time? And what's the relationship between spiking and LFP? So to develop, to answer these questions, we need to understand Fourier analysis, and that's what we started out with. And in the previous class, we were just discussing the system properties of the systems, in particular linear and time invariant systems, and the fact that those are easier to understand and analyze. Okay, and we will see why we are sticking to LTI systems in a bit. So these LTI systems can be analyzed in considerable detail, and we were going to look at the responses of these systems to two kinds of basic signals: impulse function and complex exponentials. And we had started out with the impulse functions. That's where we were. Okay, so in the discrete domain, it's easy to understand. That's a delta function is just 1 at 0 and 0 everywhere else. A unit function is 0 everywhere before time 0 and then becomes 1. And they are closely related. You can think of this as the difference of a unit function and a lagged version of it. And likewise, the unit function is just the sum of the delta function from minus infinity to n. Okay, so you're just sampling adding the values here. So if you're adding the values beyond 0, then you catch this and it becomes 1. Otherwise it's 0. That's what's shown here. Summation of interval for n less than 0 is 0, because the sum of all these dots is just 0. But if n is greater than 0, then it becomes 1. So it's actually the unit function here. In the continuous domain, it's a little bit trickier. So we have to start with the unit function. This is what it looks like. And think of an impulse function as the derivative of the unit function. Same as this. In the continuous domain, this becomes the derivative. And if you look at this, you can think of a unit function which has changes from 0 to 1 over some interval delta. Its derivative is going to be 1 over delta for this short duration, and otherwise it's 0. And the delta function is nothing but this thing as delta approaches 0. So it becomes larger and larger, and eventually it's shown as this upward arrow in the continuous domain. And the impulse function is the derivative of the unit function, and likewise the unit function is the integral of the delta function from minus infinity to t. So again, if you're integrating for t less than 0, the integration is just 0. Otherwise, it's 1. Okay. And an impulse function is something that you can think of is just, if you put an impulse function somewhere, it's essentially just going to give you the value of the function at that point. So if you put a delta function at 0, then xn multiplied by delta n is essentially just x0 multiplied by delta n, right? So this action here, when you multiply the delta function with n, it's just telling you about the value at 0. This thing holds because delta n is is 1 when n is equal to 0 and 0 everywhere else. So this thing will hold for all n. Okay, and if you shift the delta function by n0, then you are essentially sampling the value at n0. And the same thing holds for the continuous case as well. And we'll see just in a bit how it leads to what is called the shifting property of the delta function. So everybody okay still so far? This is what this is a recap of what we did in the previous class. Are there any questions? Or can I move on? Okay, you guys can hear me, right? I keep asking this.
Yes, sir.
Yeah. Okay, good. So let me just tell you one thing before we move on. This will probably make this a little clearer. By the way, I have updated the NSP course page. So you have now all the online classes as well as the PDF of all the things that we are going to do. This has some 200 odd slides. So we'll be doing this for a while. And the LFP data is here as well. So you can just click and download it. Okay, so the thing that I wanted to just sort of again re-emphasize that suppose I've got a function and this is, let's say, a continuous function. Okay, so and suppose it's it takes a value, it's a function that's 0 and well, 0 everywhere and takes a value of 5 at t equal to 1. Okay, so this is t. So this is one signal. And here's another signal. It's 0 everywhere else, and there's a delta function here. Are they the same or are they different? This is a continuous signal. It takes the value 5 here, and it's 0 everywhere else. Anyone?
They are different.
In what sense are they different?
In the above case, the y value is fixed, but at that at the point, suppose t minus x in the lower graph, the value is undefined.
Yeah, well, it's not. Yeah, it's undefined in a way that is still understandable. In the sense, it's a delta function whose magnitude is 5 units. Okay, so what about this function, which is 0 everywhere, including 1? These two are different, right? You would say they are different. Correct?
Yes.
But actually it turns out in the way we are going to develop things, these two are not different. Okay. So it's important for us to actually think about a signal like this. So this is a continuous signal which takes a value of 5 at a given point. So tell me what xt dt is going to be, let's say from minus infinity to infinity, when xt is given by this formula. What is it?
5,
0.
Yeah, that's right.
So,
So a function like this, which is just taking a particular value at just one time point and is 0 everywhere else, the integral is actually 0. The reason is that you can think of this as a small pulse of thickness delta. And then what's the area of this? The integral is just the area under this, right? What is it?
It's
It is
0.
just 5 times delta. And when delta goes to 0, this goes to 0. When we actually talk about, so this is more than what I'm going to cover here. But when we have a signal and we do its decomposition and reconstruct the signal back, we often talk about the difference in the energy between this signal and that signal. That's actually given by xt minus yt whole square dt. Okay, we won't cover this, but I'm just letting you know this is what is called L2 convergence or square. This is the energy of the error signal. This thing is actually zero. Yt only differ at one point. So it's just going to be 5 square there. And this is actually 0. Okay, so a signal, a continuous signal we just take some value, 5 here, for example, has no weight. It's as if there was nothing there because the signal has only changed for an infinitely small time. However, if xt is like this, x2t, oops, sorry. Can I write this? No. So if x2t is given by this, the integral of, let's call this x1. What's the integral of that?
1.
No, it's 5 because the delta function has a value of 5. So it is 5 delta t dt, right? Sorry, t minus 1. This signal is 5 multiplied by delta at t minus 1. When you integrate that, this whole thing becomes 1. So it's 5.
Sir,
So
does this work something like the Dirac's delta function?
this is the Dirac delta function.
Okay.
What else?
Okay.
So it's, even though it takes a infinitely large value here at 1, its integral is 1. Okay, so when you say it's a delta function of value 5, it means that the integral is 5. It's not, these numbers do make sense, even though it shoots up to an infinitely large value. They are still manageable in the sense that if you integrate them, they give you a unit area. Okay, so a delta function puts weight on the signal. Even on a continuous signal, if you put a delta function, that means you are adding weight to the signal. A signal which doesn't have delta functions, even though, let's say I have a ton of, it's signal that takes 5 at many different values, it still has no weight. The integral is still 0 because, it's all just this plus delta t and all that. Even if a function takes 5 for all rational numbers, is what I discussed in the previous class a little bit. The integral, the Lebesgue integral will still be 0. So delta functions are not some, they have meaning. They add weight such that the integral is well defined. Okay, it's an important distinction. Don't think of it in the discrete case, the distinction goes away. In this case, it's 1. So you might just say that, hey, sorry, there, this integral here is 1. So you will say, okay, that has some weight here, but the equivalent, to put the similar amount of weight, you have to actually put a delta function. Because otherwise, the signal has essentially no energy, and it's no different from having no signal at all. Okay, as we dig into the delta function more, this will become clearer. I just wanted to discuss this now so that you can appreciate the use of a delta function. This will become clearer as we go along. Okay, so let's get back and ask, why do we care about a delta function? So in the discrete case, it's very easy to understand because any signal can be represented as linear combination of delayed and scaled impulses. Okay, so let's look at this. So suppose this is any signal, any discrete signal. It's taking values, some random values like so. You can always think of this as a sum of a bunch of signals, which is taking, let's say, minus this value, x of -2 at -2 plus x of -1 at -1 plus x of 0 at 0 plus x of 1 at 1 plus x of 2 at 2 and so on. Right? So I have just divided this signal into a bunch of delayed impulses. And these signals can be well described like this. So x of -2 multiplied by delta function of x n plus 2 is this whole signal, because this is this property here, this property, nothing else. So I've just put the value of -2 here. -2 here, n0 is -2. So this is x of -2 delta of n plus 2. That's this thing here. Plus this, plus that, plus that, plus that will give you the signal. So this is how it's written in a compact form. It's a summation from k going from -infinity to infinity of n minus k multiplied by xk. And this is the shifting property in the discrete domain. Any signal can be represented as a sum of an infinite sum of delayed impulses and the value of the signal at the where the impulse is. Okay, is this fine? This one is easy to understand. The continuous version of it is harder. Is this okay?
Yes.
Yeah, okay. So if this is the case, now this is why a delta function is so interesting, is that if a system is actually linear and time invariant, then the linearity tells me that whatever is the response to just an impulse, the response to a delayed version of the impulse is just going to be the same response delayed by the same amount. This is what time invariance tells me. And linearity tells me that if I add all these things up and look at the responses will also get added up in the similar way. Okay, so this is the cool part. So suppose the output of the delta function is h of n. We'll call it the impulse response function. It's the response of an impulse function. Now, due to time invariance, if I delay the delta function, its output is simply a delayed impulse response function. If I give you delta of n minus k, the output is going to be h of n minus k. So if you add to, so this is because of time invariance. Now, because of linearity, if my signal is like this, the output yn is just going to be this. I've replaced the delta function here with the impulse response function. So this is actually awesome, because all you have to do in order to characterize the system completely is to find out what the impulse response function is. Hn describes the system completely, because you can now predict the output of any signal xn. If I know Hn, I know the output of any signal xn, it's given by this formula. Okay, and this is an operation called convolution. Does anybody see any similarity between this and something else that we have done previously?
Cross correlation.
Cross correlation, very good. Yeah, so except there's a minus here, there's a plus there. Okay, so convolution and cross correlation functions are related. and we'll see later in the frequency domain, they become even more well, easier to understand. So, but you know, this formula here for now is called convolution, and it is you know, somewhat related to the cross correlation function, where we did xk multiplied by hn plus k. Okay, so I'll show you an example. This you know, if I give you a signal and it's an LTI system and you know its impulse response function, all you have to do is convolve the signal with the impulse response function and you get the output. It's as simple as that. So here's an example. It is taken from Oppenheim and Bilski. So suppose the impulse response function is the unit function. What does that mean? That if I give an delta function to the input as an input, I get Hn as the output. This is the response of the system to a delta function. And now I ask, suppose I give you a signal which is not a delta function, whose output is Hn, but a signal that becomes zero at becomes this alpha to the power n at 0. So for 0 it is just 1 and then decays like this. And I'm asking now, given this signal, what is going to be the output? Okay, and now you will say no problem. I will just find out using this convolution method that I have learned just now. How do I do it? Xn, so we have to just evaluate this and then sum this up. That's all we are doing. Evaluating this and summing it up, right? So I keep xk the way it is. This is now the k axis. And I flip the second signal. This is hn or hk if this is the k axis. This is h of minus k. And h of n minus k is just the signal that is shifted, which is shifted by n units. Hn minus k is shifted by n units. This is h1 minus k, this is hn minus k. For n less than 0, it's shifted this way. Okay, so this is again that scaling business. When you have positive numbers, it shifts this way. When it's negative numbers, it shifts that way. You know, so I'll let you guys think about which way it should shift. You know, this is the correct A. So what I'm doing is when I want, let's say x1 h, xk h1 minus k, I'm taking this thing and multiplying it with that. And that will just catch this alpha to the power k and the values between 0 and this. So this is xk multiplied by hn minus k. It will just have these many values here. Okay, is this making sense? It's sort of hard for me to do this here. Oh, I can write here. Oh, I didn't know that. Okay, is this fine? It's basically, when I do this, it's just taking the values between 0 and n. Otherwise, it's 0. Because only between 0 and n, you've got both the things as non-zero. Otherwise, it's all 0. This is okay, right? So the summation.
Sir.
Yeah.
So the output function is predefined or it is obtained from that convolution?
No, yeah, so I haven't done the convolution yet. Right now, I'm just telling you the product. And the product is going to be this. If your n is less than 0, like this, then the product of this and this signal is just 0. Right? That's a no-brainer.
Yeah.
When n is positive, then it's non-zero only for values of k between 0 and n.
Okay.
Okay, and to do the convolution, I have to now sum this up. That's this. But the summation is only between 0 and n because it's 0 everywhere else.
Yeah.
Okay, and this is a geometric series. So the solution is just that, and this is the output of the function given the input is this. Okay, and this is how it looks like. Okay, so this is like an integrator function. It's a function that integrates. So when you get a delta function, you get a unit response. And this is like the integration of the signal. This is how it will look like. So now that I have told you that the impulse response function is this, you can find out the solution to any xn. It's just actually this, something of this form. Okay, any questions on this? Am I going too fast here or is this okay? Okay, I'll take this as a yes. Huh? Yeah, tell me.
Just read. So I'm still not getting why do we define like a to the power k is has the value on the a to the power alpha has only the value from ranging 0 to n only, not means how do we define that? Means
Well, so x of k is this function. It's defined for all positive values. But you're multiplying it with h of n minus k, which is 1 for only a limited number of values and 0 everywhere else. So when you take the product, you can only count for these many values, not anything else, right? So it's just going to be x alpha to the power k for these, and it's going to be 0 everywhere else. That's it. Does that make sense?
Yeah.
Okay. So that's the output for signal xn given by this. And once you know the impulse response function, you can find the output of any x. Okay, so now let's do the same thing in the continuous domain. This is a slightly trickier version, but essentially we will make the summation into an integral. That's what we are going to do. So suppose I've got a continuous signal like this, x of t, and I want to know what happens when this x of t is passed through a LTI system whose impulse response function is h of t. Now they are all continuous. H of t is a continuous function, which is the output of an impulse response function. Output of an impulse function. So this is the impulse response function in the continuous domain. And I'm asking if I've got a LTI system and I pass any signal x of t, how it's going to look like. So here's what I do. I look at the signal and I divide it into small rectangles like so. So by the way, all of this is taken from Oppenheim and Wilsky. They explained it so beautifully that all I had to do is just copy paste their figures. So I heavily recommend reading it carefully. Even if you don't want to do this kind of stuff, it's just so pleasing, so nicely constructed and explained. It's really a pleasure to just read it. So I recommend doing that. So, okay, here's what I'm doing. I'm dividing it into small rectangles and calling this signal, continuous signal, as a sum of all these rectangles. Okay, they have a distance between them is delta. So this is minus delta, NS2 delta, and so on. And the value is likewise x of minus n delta. Okay, so I'm defining my delta function as this, like before. As delta approaches 0, this will become a delta function. And my continuous signal is essentially, well, so this is the discretized version of the continuous signal. This x hat t is this this sum of rectangles. So this below the continuous function, this jaggedy square rectangular line is this function. It's nothing but your shifted delta functions multiplied by the value of the function at this. One of these is this. Okay, and you are multiplying by delta, so that's this whole thing, and then you are summing all of this up. Okay, and as delta approaches 0, this function approaches the actual continuous signal. Make sense? This is fine, right? So now I ask that what happens when delta approaches 0, and look what is happening here. As delta approaches 0, I can think of this now as an integral, where I am changing this to a continuous variable. So this delta is becoming 0, so it's essentially becoming d tau here, and this is becoming x tau, and this is basically becoming a delta function sitting at tau. Okay, and this is the shifting property of an impulse response function in continuous time. When I put a delta function at some value, in this case it's a delta function sitting at t, and I integrate the entire signal, I get the value of x at t. Is the same as what we have done here, which was the shifting property at it's not shifting, by the way. I've seen people call this a shifting property. This is shifting. Shift is this you have this way to remove when you have cement and you want to remove particles, you go through, or you take a sift and you shake the thing, and the bigger pieces of rocks get sifted out. It's in that sense. We are sifting the signal. We put a delta function, and wherever we have the delta function, that part gets sifted. The rest is sifted out. Okay, so this is the shifting property of an impulse response function, of an impulse function. A delta function, you put it somewhere. So if I have got this signal and I have put a delta function at 5, and I integrate it, I'll get the value of the signal at 5. xt. Okay, is this okay? This is slightly harder than the discrete one, but this is the is the same principle here. I'm shifting the signal, and I'm writing the signal now as a product, as an integral of delta functions. Okay, and then it's very easy for me to understand how the system is going to respond when I have any x. How do I do that? Well, it's the same logic as before. So suppose a signal like this, x0, a little pulse like this, produces an output that looks like this. Okay? And a shifted version of this produces a different output. A shifted version of that produces a different output. This is right now a system that is not even time invariant, because depending on where this signal is, the input is, I'm getting a different output. So this is a very generic case. This is a case where the impulse response function is dependent on the position of the signal. H0t, H delta t, Hk delta t, they could be different. This is the most generic thing that you can think of. The output is just the sum of these guys. When the input is this, I'm again breaking it down into small pieces, and the output is just that. This comes only from the linearity property. Right now, it is a generic system which is not time invariant, but it's linear. Linearity gives you this, and when delta approaches 0, this turns into this integral here. Now, in addition, this note that h tau t is the response of a delta function that's sitting at tau. However, if it is a time invariant system, then a shifted version, the impulse response at tau is just going to be a shifted version of the impulse response at 0. This comes from time invariance. So for a time invariant system, the output is just this, where ht is the impulse response function in the continuous domain. And this is what is called convolution in the continuous domain. Same logic as before, nothing has changed. So as long as you know the output of a delta function, ht, you can find the output of any signal xt just by convolving it with the impulse response function. That's it. So we'll look at the same example as before, but now in the continuous domain. So suppose I have got a continuous signal xt, which is equal to e to the power minus at ut. So it's 0 everywhere, and then it takes a value of 1 and then decays off. And suppose the output of the delta function is the unit function, like this. So this is the response of an LTI system when you pass a delta function through it. This is the impulse response function. Now when I do x tau ht minus tau, again for different values of t, I'm showing this function. When t is less than 0, I have flipped this h tau and made it h minus tau, and then there's a t here. So this is when t is less than 0, this is when t is greater than 0. And obviously, when t is greater than 0, I'm looking at this thing here. Right? So from 0 and t, values of tau between 0 and t, this is the value, e to the power minus at, otherwise it's 0. Same logic as before. So this is just x tau ht minus tau. If I take the integral of it, it's just e to the power minus a tau d tau. Take the integral, this is how it looks like. And there's an uncanny similarity between what we had seen earlier in the discrete version. And that's how it should be. So this is the output of a signal that looks like this, given the impulse function, response function that looks like this. Okay, any questions on this? Everyone is happy? Okay, so I'll take this as a yes. So we have covered the first part, which is our understanding of a delta function and of convolution, which is a very important operation. And we have explained, we have understood why a delta function is so important, because for an LTI system, all you need to know is the response of the delta function, the output of the delta function, the impulse response function. And then you can answer, no matter what signal you give, you know what the output is going to be. So you have actually described the system completely. Okay. So the convolution function has very interesting properties. If I've got two functions, xn and hn, I could change their order and this will hold. It has this distributive property, it has this associative property and so on. So I won't cover this. It's very easy to understand. So let's say if I, and these by the way also hold in the continuous domain. So xt convolved with ht is the same as ht convolved with xt. So this is very easy to understand. So if I go back here and look at the formula, xk h n minus k, right? So, well, let me just do this. Though, so I'll come out of discard. So this is very easy to understand that hk hn convolved with xn is just, that's it, right? Where k goes from minus infinity to infinity. So now all you have to do is just change the call m as n minus k. So then when k is minus infinity, what do we have here? M is plus infinity, right?
Plus infinity.
When k is plus infinity, then m is minus infinity. So I could just might as well write this as, and the summation, it doesn't matter whether you're going from minus infinity to infinity or the other way around. So it's just, xm here. And what do I have here? What is now k? What is k in terms of n and m? K is just this, right? M h n minus m, which is your x. Okay, so just the change in variable here, and you can see because the order doesn't matter here, it's the same whether you write it this way or that way. Okay, so this is the commutative property. Likewise, you can see that if I've got hn and I'm convolving it with x1 n plus x2 n, then you will have two terms here, but they will just branch out and you will end up getting the individual sums. So I will leave this as an exercise, not super difficult. But all of these properties are easy to verify. You can do that yourself. Okay. So before I move on, I should tell you that just your knowledge of HN actually tells you a lot about the system. So for example, if you say that the system has to be memoryless, which means it shouldn't remember anything about what has happened in the past, or for that matter, anything in the future, then your Hn has to be 0 for any value of n that is different from 0. So it's like a delta function sitting with a value of h0 at 0. Any other system will have some memory because you are essentially summing over the past values or future values for that matter, right? So if n shouldn't depend of any value of k different from n, then Hn has to be 0 for all values other than n. So this is your memoryless property. Likewise, this is an important thing. We will keep getting to this. This is called causality. Causality means that your signal shouldn't care about future values of the output shouldn't depend on future values of x. Might be wondering why this is the case, but we'll see lots of examples where, when we look at filtering and so on, where the response is not causal. And essentially, causality boils down to having a impulse response function which is 0 for negative values of n. Remember, Hn could be anything. If Hn, like here in these examples, the system is causal, but if Hn is not takes non-zero values for negative values, you can get a response even before, you can get a response for negative values of n as well. So if you put a delta function at 0, you will get a response for values of n less than 0 if Hn is non-zero for negative values. Okay, so causality, even though it kind of seems obvious in our case, is not a prerequisite here. Hn could be anything and a system responds. So let's say Hn is 1 everywhere. Okay, that means even if you put a delta function at 0, the response has started even before the delta. It's a non-causal system. To have causality, which is very important when we talk about brain signals, because we want to know which signal caused which signal and so on, you need to have Hn equal to 0 for n less than 0. Okay, so this is a causal system. There's also, you can look at invertibility and stability. I'm not going to talk about these things, but I encourage you to look this up in Oppenheim and Wilsky. Looking at whether this integrates properly or not, you can find out if the system is stable, which means that for finite input, you get a finite output. And also you can talk about invertibility, which means that given yn, can I find out what xn was, which in a way is like inverting the response function. Okay, so we won't talk about these, but you can read this up. Won't not essential for this part of the way we are doing this course. Okay, so this is as far as I have about impulse functions. If there are any questions, now's the time. Otherwise, I'll talk about something, the complex exponentials next.
Sir.
Yeah.
For time invariant system, so Hn is on. So is there any other leaving the unit function? Is there any other Hn functions which are used in invariant system?
No. See, right. So whether a system is LTI or not, you cannot determine that by looking at this function. Okay, so HT could be anything. It could be like this function, it could be a sinusoid, it could be anything. Okay, so when I say that it is LTI, what it means is that if I shift this signal, then the output, the H is going to shift. And if I add a bunch of these signals to construct another signal, the output is going to be the sum of those. Those things have to be told to you.
Okay.
If I tell you it's an LTI system, then you use this formula to get the output. If it is a time varying system, then you use but a linear system, then you use this formula. Okay, now LTI system is allowing you to use this formula. It has nothing to do with what HT looks like.
Okay.
Okay, HT could be anything. It's just that you won't be able to use this formula if it's not a LTI system. And then HT will have no meaning. HT is still the impulse response function. It's the output of a delta function. But it will have no meaning because if I shift the delta function, the output is something else, which is what I'm showing you here. This is a non-invariant system. For an LTI system, the HT is just going to be a shifted version of this signal only. It can't be anything else. Okay, so just by looking at the form of HT, I can't tell you whether the system is LTI or not. LTI is something that I have to tell you that, okay, this is an LTI system, hence computing HT is of some use. So you insert a delta function, get an HT, and if it is LTI, then I can use this formula and get the YT for any XT. If it's not LTI, I can't use this formula.
Okay. I'm not able to visualize, like, if let's say, like, it's a time invariant system, then how, if h of t is also shifted, then how the convoluted part would look like in a graphical way.
In the graphical way, this is well. So in the graphical way, if I shift this delta, you are going to see the same shape. You are going to see the same shape. This shape shifted by this.
Right. Now it's clear. Yeah.
Right.
Correct.
This is time invariance. So this is the time invariance property.
Got it.
Okay. All right. Any other questions? So I'll just give you a very brief outline, and I want you guys to think about this. So see, we have done the delta functions. So we have described the signal, response of a signal. We have described the system properly using delta functions. Why do we care about another type of signal? So I am considering now impulse response function and another type. Why do I even care about this? And this is actually the key reason why we do Fourier analysis. So the idea is that, look, when I gave a delta function here, when I gave a delta function, I got an output which is not a delta function, some other shape. HT here is, when I give a delta function, it is some other shape. It could be a triangle, it could be sinusoid, it could be blah, 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 whatever. But I can now ask another thing, that is it possible for me to give a signal such that the output is the same signal, just multiplied by something else? Turns out a complex exponential is such a signal. When I give a complex exponential as an input, I'll get the same complex exponential as the output, just multiplied by some number. And it's a complex number, so it will change the amplitude and phase of the complex exponential. But you can't get something else. You can't get a triangle, you can't get a delta function, you can't get anything else. The output, the response of an LTI system to a complex exponential is the same complex exponential with only a change in amplitude. Okay? We will do this, why this is the case, in the next class. But suddenly this makes this whole thing very cool, because once I look at the input, my output has the same form. It's just a scaled version of the same thing. So in terms of linear algebra, people who may have heard these terms, you can think of it as an eigen function of the LTI system, where these are the eigenvalues. Okay, an eigen function is essentially the same thing. Ax is equal to lambda x. A is the operator. It's like something that it does to x. But if it is an eigen function, if x is an eigen function, then Ax is just lambda x. You get x back, it's just multiplied by some value lambda, which is called the eigenvalue. So this motivates why we do Fourier analysis, because essentially Fourier analysis is just taking a signal and representing it as a bunch of a sum of complex exponentials. That's it. And then the nice thing is, once you divide the signal into a bunch of complex exponentials, the output is going to be just the same exponentials, each multiplied by some number. And if you find that number, which is what the Fourier, the output of the Fourier analysis is, you can also describe the signal perfectly. Okay, so this is why we are going to now go to the next part and look at how LTI systems deal with complex exponentials. That will be the, that will be what we'll cover in the next class. Okay, I am done. So as always, I will stop recording now and stop sharing, and I'll take questions. People who are have other classes are free to leave. So I'm done for the class today. Done with the class.